these multi-resolution approximations are very special because they generate approximations in a nested manner and in a hierarchical manner. Not only that, these multi-resolution approximations, which are very important in computer vision, are also useful in developing a fast algorithm for computing DWT. So, let us look at the brief theory of MRA, and that is what we will conclude the lecture with. Before even we talk about approximations, all along we have been using this term approximation, but it is time to just review formally what is meant by an approximation in vector algebra or functional analysis. In general, we understand what an approximation is, right. It is some estimate of the signal, and it will always be in some error. So, any approximation that I construct will have some error. Therefore, there are infinitely different ways in which I can construct an approximation depending on what I want the error to satisfy, that is what characteristics the error should have. From an optimal viewpoint, that is if I want an optimal approximation, I would say find an approximation that minimizes the 0 norm of the error or 1 norm of the error or even the infinity norm. So, I have x of t, I have x hat of t as an approximation. For the moment we are not talking about MRA, we are just talking about some approximation. X minus x hat is some error, and I can say find x hat such that the error has minimum 2 norm or minimum 1 norm and so on. Generally, what is of interest is the approximation that yields the best 2 norm or the minimum 2 norm of the error. And that is what we mean by best approximation here. In other words, I want an approximation x hat of t of a signal or a function x of t such that the 2 norm or the energy of x minus x hat is a minimum. It turns out that the solution to that problem is that the approximation x hat, optimal x hat, is nothing but the so called orthogonal projection of x onto what? Onto the basis that generates x hat. Okay. First, let us understand what is orthogonal projection, and then the statement will become clearer. What is an orthogonal projection? If I take any vector x which is in a vector space for which the inner product and the norms are defined, then the orthogonal projection of a vector x, projection is always about projecting a vector onto some other subspace, right. So, I am here projecting a vector x for which a norm exists for which I can compute inner products onto a subspace. So, recall the analogy that we had, walking on the road or a person, a 3D object whose shadow is on the 2-dimensional road or the floor or wall and so on. So, you can think of x living for example in a 3-dimensional space, and you are projecting that onto a 2-dimensional space. So, n is 2 here for us. In general, x lives in some space and we are projecting it onto a lower dimensional subspace M, which are spanned by these basis functions. Recall in unit 2 we had given some definitions, basic definitions of linear algebra, what is a span, what is a basis and so on. Then the orthogonal projection is nothing but a linear combination of the basis functions with the coefficients of the linear combination derived from the signal. So, P subscript m of x always denotes orthogonal projection of x onto the subspace M, which is spanned by the basis functions phi. So, this is nothing but x hat actually. So, Pm of x, that is what we meant earlier, but we will talk about it. Right now we are only talking about projection. So, if I give you x and if I give you the basis functions phi, the orthogonal projection is calculated with the help of equation 10. Where the coefficients are computed by solving these n equations in equation 11. How do I get this equation? Let me quickly show you that. So, I have x of t living in some subspace, some space V, and we are breaking this up into an approximation plus some error. All right. Orthogonal projection has this speciality we call orthogonal projection OP. The main feature of the orthogonal projection is that the inner product between epsilon and x hat is 0. So, the inner product between epsilon and x hat is 0, and x hat itself is generated by projecting x onto M, and M itself is spanned by this basis functions phi, right. Therefore, this is a span of the basis. So, we are saying some combination of the basis functions in the space M will generate an approximation of x, right. Now, I plug this into here, and then I use this result, right. So, what I do is I take inner products of x with x hat of t. The only step that I do is, instead of taking the inner product of epsilon with x hat, I take inner products of epsilon with the basis functions that generate x hat. It is one and the same. Therefore, I require this. And once I write these equations, I get those n equations that you see in equation 11, right. So, what I do is I take inner product of x of t with phi I, on the right hand side I have, so let me use a different dummy variable here so that you are not confused. The second term goes to 0 by our orthogonal projection requirement, and therefore, I get these equations. And I let j run from 1 to n. Now, the big advantage of choosing an orthonormal phi, in the original statement the phis are not orthonormal necessarily, but they are a basis, which means they have to be linearly independent. But now, if I require that these phis are orthonormal, that is the inner products are either between similar basis function, identical basis function is 1, or if they are not identical it is 0, then the coefficients can be readily computed. That is the big advantage of orthonormal. If you look at equation 11, so I have n equations in n unknowns and I have to perform matrix inversion. But if the phis are orthonormal, then I can solve coefficients individually, and that is the big advantage of choosing an orthonormal basis. So, the equation 12 is a much simpler version of 11 because you are only solving for the individual coefficients, there are no inversions involved, right, and that has come about because I have assumed phis to be orthonormal. Now, let us return to the best approximation situation. The statement essentially says what we have said earlier, the best approximation of a vector x using basis functions that is of x living in a vector space obtained by projecting it onto a subspace M which are spanned by basis functions phi is best only if it is a orthogonal projection. That is, if I have a signal x and I want to construct a best approximation of that using some basis functions, then the best approximation in the least square sense, in the 2 norm error minimizing sense, is nothing but the orthogonal projection itself. Therefore, the best one is x hat sigma ai phi I, exactly what we have seen on the board earlier. All I have done is I have assumed if phi is orthonormal, then I can use equation 12 in place of ai's to construct my orthogonal projection, and that is what exactly I have. So, let us look at an example quickly. So, the best approximation of x, suppose I have a vector, all this is equally applicable to both functions and vectors. I have a vector x here 1 2 3 transpose living in the 3 dimensional real space, and I want to approximate this vector with 2 basis functions only, which means now these 2 basis functions are orthonormal, as you can verify. They span a subspace of R3 because there are only 2 basis functions here. They span only the 2 dimensional subspace, they are orthonormal, so they are basis, but for a subspace of R3. So, I want to obtain an approximation of x onto this 2 dimensional subspace spanned by phi 1 and phi 2. By the above result, the best approximation is this here, where AI's are given by these coefficients here. In other words, approximation itself is x hat. These AI's are called the approximation. In the world of wavelet transforms, one of the key things that you should be distinguishing is between approximations and approximation coefficients. Okay. AI's are called approximation coefficients, they are called a signal representation in this subspace M, and x hat is the approximation, alright. So, that is what we will do. Now, we will extend this idea of approximations to multi-resolution approximations. What is multi-resolution approximation? It is also an approximation, but it is a collection of approximations over different spaces. Just now we spoke about approximation onto some subspace M, but now we are going to talk about approximations on several subspaces. And what is so special about these subspaces? These subspaces are spanned by basis functions that are defined over coarser and coarser grids. Okay. The grid from finer to coarser grids and the grid spacing varying by a factor of 2. So, there are some important features of an MRA. One, that the approximation of the function at a resolution 2 power minus m is described by set of coefficients or samples over a grid of spacing 2 power m. So, the coefficients that you are computing at a certain resolution are not defined over an arbitrary grid, they are defined over a grid which has spacing 2 power m, and at each scale the approximation is given with orthogonal projection naturally, because we are seeking the best approximation. So, what I do is to construct MRAs, I take the basis functions which are the scaling functions at scale level m and project compute the orthogonal projection of x of t over the scaling functions at that scale, alright. And further, each space, this Vm essentially is spanned by the set of preferably orthogonal basis functions. In general, these basis functions at any scale that span the subspace at any scale need not be orthogonal, but we just now saw what is the advantage of choosing orthogonal basis functions. And the last point is something that we have mentioned earlier, the coefficients at a coarser scale can be obtained from those at the finer scale, right. We have seen that in terms of approximations earlier with the sine wave example. So, in the sine wave example I did not show you coefficients, I showed you approximations. So, let us conclude the discussion with a formal definition of MRA. We will take the essence of this and the main equation and then move along. The first point says that if I look at a collection of subspaces, when can I call it as an MRA? Remember, multi-resolution approximation is a collection of approximations of a signal onto subspaces. So, what subspaces will qualify to generate multi-resolution approximation is what Mallet had prescribed long ago, and this was the turning point in the DWT. These subspaces should satisfy certain properties, and those are the 5 key properties that have been listed here. All of them are important, but I will highlight the points 2 and 3. The point 2 says that the subspaces should be embedded, okay, which means as I move down M, then I should get finer and finer approximations, and as I increase M, that is I move up in the level of M, then I get coarser and coarser approximations, and these approximations are nested, these subspaces are nested, therefore, the approximations can also be said to be nested. What nested means is given in equation 15, that is 3 really tells you what this nested means. It says that as I move from Vm, which is the subspace at level M, to a coarser subspace at Vm plus 1, Then if x of t belongs to Vm, then x of t by 2, that is dilating, here x is some function, it need not be the signal that we are talking about. So if I take any function that lives, that is spanned by the basis functions in Vm, then a dilated version of that function, the moment I dilate it, I am moving to a coarser subspace. That is what it means, and this is the fundamental equation for us. Both 14 and 15 are fundamental in deriving what is known as the scaling relation in DWT. Then points 4 and 5 are essentially saying that as I move down, as I move up, that is coarser and coarser and coarser approximation scales, the approximation essentially goes to 0, and as I move down, that is go and finer and finer and scales, the approximations will converge to the original function x of t, right. So I will be able to recover the original signal. So this ensures that spanning essentially 4 and 5 together are essentially saying that as I move from m equals minus infinity to plus infinity, I am spanning the entire real space of finite energy functions. That is what it means. So this is the last point that we will make in this lecture, and in fact this is also the transition for the next lecture. How do I use this MRA now? What kind of basis functions do I use? Can I use any scaling function? So look at what has happened. We talked about DWT in the previous lecture, and now we have moved to scaling functions, and we are talking about approximations, in particular MRA. Now what we want to know is, given these properties of MRA, how do I choose my scaling function? Do I always work with scaling functions, or is there a better way? How am I going to implement? So this is a slide that allows us to transit from scaling functions to filters, low pass filters. And the basic idea is again derived from the property of MRA. The approximation at level m is contained in the approximation at a finer level m minus 1. How do I construct approximation at level m? Well, by projecting the signal onto the basis functions that span level m. What are the basis functions that span level m? Then those are phi m of t, right, and its translates. Now this is a generic statement, m can be 0 and m can be 1, m can be 2, whatever. So if I choose m as 0, then, or m as 1, let us say, then what I am doing is I am looking at a scale 2, and then what this statement means is the approximation at level 1 is contained in the approximation at level 0. That means in terms of basis functions, the basis functions that span the subspace V1 can be generated by the, or can be spanned by the basis functions that span V0, right. What are the basis functions that span V0? Phi of t and its translates. What is the basis function for V1, the subspace V1? Phi of t by 2, because V1 is a subspace that is essentially a dilated version of the functions in V0. So if phi of t, if I am looking at m equals 1, then I have phi of t by 2 at V1, the basis functions, and phi of t for the basis functions for V0. So this statement essentially means I can take any function in V1, including the basis function, and express it as a linear combination of the basis functions at a finer resolution. By fixing m equals 1, what I have here is V1 and V0, and I am relating the basis functions for V1, I am expressing the basis function in V1 in terms of the basis functions at V0. In general, you can also write this relation. So let me do that on the board for you. So what the statement essentially means is V1, the basis functions for V1 can be spanned by basis functions for V0. In general, for Vm, basis for Vm can be spanned by the basis for Vm minus 1. So what is the basis for Vm? the basis for Vm, the subspace Vm is nothing but your phi 2 power m n of t, and basis for Vm minus 1 are phi 2 power m minus 1 n of t. So, what we have done is we have set m equals 1 and written that equation. We have said the basis, well, although I have written here phi 2 of 2 power m, we know that phi 2 power m is nothing but scaled version of phi. So, phi of t by 2 for example, in fact when I move from phi of t to phi of 2 power m, then that is nothing but 1 over root 2 power m times phi of 2 power minus m t minus m. Because m equals 1, we have 1 over root 2 and I am picking any basis function for V naught. In fact, I can write another basis function also in V naught, which will be the translate of 1 over root 2 phi of t by 2. I am just saying one basis function, any basis function in V naught, which is 1 over root 2 phi of 2, can be expressed as a linear combination of the basis for V naught. V naught basis functions are phi and that is what we have essentially. So, these h are the coefficients that allow me to go from V naught to V 1, all right. And how are these coefficients obtained? They are obtained by taking the inner products of phi of t by 2 with phi of t minus n. That is again by our assumption that phis are orthonormal, right. So, all I have to do is that, and that is the beauty here, because we have assumed phis to be orthonormal, there is a slight mistake there in equation 16, it should be t minus n, not t minus k. Because phis are orthonormal, the coefficients are obtained by simply taking the inner product between 1 over root 2 phi of t by 2 and phi of t minus n. Now, what you see here, the equation 16 is actually looking like a convolution equation, but there is a difference. On the left hand side you are not obtaining some function of t, but you are obtaining function of t by 2. So, there is a convolution followed by some downsampling, right. In fact, exactly downsampling by a factor of 2. So, this is different from the regular convolution and this is what we will notice in the pyramidal algorithm. But for now, what is important is to remember that these coefficients h are nothing but our low pass filter coefficients. Why these are low pass filter coefficients? Because what we are doing here, as we go from V0 to V1, we are constructing another approximation, but a coarser approximation, and approximations are always generated by low pass filters. So, the most important point is that instead of talking of phi of t's, which becomes boring or difficult later on, we shall talk in terms of this h, which are the coefficients. So, by specifying the low pass filter coefficients h here, I would be indirectly specifying phi of t itself, and we will look at all of this in the next lecture. That is essentially the connections between scaling functions phi of t and the filter coefficients h of n. And also remember, we have talked about approximations, but to complete the picture we need the details. So, we need to bring in the wavelets as well. So, how do we bring in the wavelets so that the picture is complete and that is where we will end up looking at the high pass filters and eventually put together the complete picture for us, right. Okay. So, we will meet in the next lecture where we will talk about connections between scaling functions and filters and also the connections between wavelets and filters, and then discuss the pyramidal algorithm that is used in, or the fast algorithm that is used in computing DWT.